previous lecture we had talked about the objectives of the finite element method, where it is used in an engineering analysis, and what are the basic steps involved in a typical finite element analysis. In this lecture we are going to develop our understanding of the method a little further by looking at a typical model problem, and for that model problem we are going to develop the so-called virtual work formulation. After the virtual work formulation has been developed, we will also discuss another concept called the concept of a functional, and using the functional we are going to develop something called the variational formulation, and we will show that for at least this model problem of interest, both the virtual work formulation and the variational formulation are the same. Finally, we are going to take the variational formulation, and with respect to this formulation we are going to develop a method called the Ritz method. So we will develop the variational formulation, which we are going to apply to the model problem that we will consider, and we will use a method called the Ritz method to obtain a solution to this model boundary value problem. The Ritz method is going to be used here because it is the precursor of the finite element method. So let us take the model problem that we had also discussed in the previous lecture. This is the extension of the axial bar. Now if you look, the problem has been complicated a little bit, wherein we have added now a variable cross section to the bar. So the bar has a variable cross section. It is loaded by a distributed force Fx and an end load P at the point x equal to L. At the point x equal to 0, the bar is fixed. That is, the displacement at this point is set to 0. So if I now write the model problem in a detailed form, the boundary value problem can be given as equation 1a, where we have the differential equation given by minus d dx of Ea, which is now a function of x, du dx is equal to fx for all points lying in the interval 0 to L. U is the displacement of the bar. With the boundary conditions, as I have already mentioned, u at the point x equal to 0 is equal to 0, and the force at the point x equal to L, I, Ea du dx evaluated at the point x equal to L is equal to the applied force at the end L equal to P. For the model problem given earlier, let us now take the differential equation and move both terms to one side. That is, we will get minus of d dx of Ea, which is a function of x, du dx minus f of x is equal to 0. This term that we have put on the left hand side is called the residual. Now what we are going to do is, we are going to take this residual and multiply it by a weight function Wx, that is any function Wx which is admissible. We will define admissibility later on. So what do we call this? So residual, let me call it by something Rx. So residual is a function of x given by Rx. So I take Rx, multiply it with a function Wx, and then I integrate it over the interval. So obviously this integral is going to be equal to the integral of the right hand side, which is equal to 0. So when I take this, the integral of the residual multiplied by Wx over the whole domain, that is x equal to 0 to L, this is called the weighted residual formulation. Now the question is, what do we mean by this weight Wx? Let me reiterate. This Wx is given a name, that is a weight function. Now this Wx, as we will see later on, has to satisfy certain minimum smoothness conditions in the domain and certain other conditions on the boundary of the domain. Now many people use this weighted residual formulation that we have written here to solve the problem. What we are going to do next is that we'll take this weighted residual and let's expand it and write it again. So in the expanded form, this becomes w dx minus integral of x equal to 0 to L fw dx is equal to 0. Now if you see that in this term, the second derivative of u is sitting. So what we would like to do is pass one of the derivatives from u to w. That is, we are going to do an integration by parts for this term. So I integrate this term by parts. To get EA du dx dw dx, and I'll take the required terms on the right hand side. So this will be equal to x equal to 0 to L fw dx plus, if I look at it, EA du dx w evaluated at point x equal to L minus the value evaluated at point x equal to 0. So what we have done, we have integrated this term by parts, which gave us a volume integral part, that is in the interval, plus a part which is the boundary term. So next what we are going to do is, we will look at this boundary term, which is EA du dx w evaluated at the point x equal to L minus EA du dx w evaluated at the point x equal to 0. So if you look at this, this is the boundary part or the boundary term at the point x equal to L, which is the right extreme of the member that we have taken, and this one is EA w du dx w evaluated at the point x equal to 0, which is the left extreme of the member that we have taken. Now in the model problem that we have taken, at this end EA du dx is the force given by a value p, while at the end x equal to 0 EA du dx is an unknown term, but at the end x equal to 0 u is known. So what we are going to do is, at the end x equal to L, where the force is given, we are going to let w be free. That is, we do not put any constraints on w at this end. While at the point x equal to 0, we are going to enforce the constraint that u is given equal to a value 0 by making w is equal to 0 here. So when we make w equal to 0 here, this term vanishes. So what we are left with is the following formulation: integral x equal to 0 to L EA du dx dw dx dx is equal to integral x equal to 0 to L fw dx plus p w evaluated at point x equal to L. Okay, so this is the formulation that we get. So once we have obtained this, next what? If we stick to this formulation, this is in a way enough to work with. But what we would like to do is to set it in our mechanics framework. That is, we are going to choose W to be not any function of interest, but a function called delta U of x, where delta U of x is said to be the variation of U. So let's imagine that I'm giving you 2 points, x equal to 0 and L. In between this, I have this function U of x, and on top of this, if I take a function which is close to this, it cannot be very close, it can be anything which is close to this function. Now we have to define what we mean by close. This function we are going to call as ux plus delta ux, okay, such that the difference between the two functions is the function delta ux. So whenever we are talking of this variation of u, it is as if I am taking a function in the neighborhood of the function u and taking the difference of those, that we can call as the variation of the function ux. So if I take wx equal to the variation of the function ux and put it back in our formulation that we have obtained by doing integration by parts, then we'll get f delta u dx plus p delta u evaluated at the point x equal to L. This is something that we are familiar with. This part, if you look at this part, this is also equal to the stress in the bar sigma x due to the displacement of the bar. This part we can say is the strain due to delta u. And the right hand side, if you look at it, is the work done by the delta u against the distributed body force F and the end force P. So what do we have here? We have something called the internal virtual work, and this is virtual work done by the external forces. Now why do I call it virtual work? Because our equilibrium has been achieved under the action of the forces F and P, and we have obtained a displacement field U, a corresponding strain field Ex, and a corresponding stress sigma x. Now we imagine that from this equilibrium state we are going to perturb the system by a small amount delta U. This is the variation of U that we are talking about. So this is called a virtual displacement if I want to give it a name. So delta U is a virtual displacement. Okay. So this, the term that we have here on this side is the work done by this, the strain due to this virtual displacement against the stress that has been built up in the bar to counter the effect of the external forces, while on the right hand side it is the virtual work done by the virtual displacement delta U against the external forces that we have. This, if I take this equation, this is given a name. This is called principal of virtual work. This whole formulation is also called by another name, which is the weak formulation. Question is, why do we call it a weak formulation? It is called a weak formulation because if you look at the first integral on the left hand side, here we have taken one of the derivatives from u and transferred it to delta u or the w that we had taken earlier. So what happened in the differential equation, we required the second derivative of u to be defined because it was a second order differential equation, and at every point in the domain we had to have definition of the second derivative of u. While in the initial weighted residual formulation, if instead of w I had put delta u, all that was required was delta u has to be defined in order to have this integral finite. But now if you look at this term, we only need the first derivative of u to be defined. That is, instead of asking for the second derivative to be defined, we are now requiring only the first derivative of u to be defined, which is a weakening of the smoothness condition on u. That is, all we need is the first derivative of u should be given. Similarly, we have now transferred the derivative from u to delta u. That is, now we want the derivative of delta u to also be defined in the domain. That's why we call this a weak formulation. Next, let us now look at the properties of this variation delta u that we are going to use in our formulation in future. Okay, now let us look at the conditions that our delta u or the variation of u has to satisfy, or the virtual displacement has to satisfy. You see, at the end x equal to 0 for our problem, we have u given. So when u is given, the variation of u is set to 0. So at a boundary where the displacement is specified, there the variation delta u is set to 0. That is the first condition on delta u or on w that we had taken, the weight function w. Second, what we have done is we have not put any condition on delta u at the end x equal to L. That is, at the boundary where the force is specified, Ea du dx for example, in our case at x equal to L, we will let delta u or w to be free. They can take any value that you wish. Third, as we have shown in the weak formulation or the principle of virtual work, all we need is that the derivative of delta u should be defined in the domain. So when the derivative is defined, then the integrals that we have in the variational or the virtual work formulation or the weak formulation are all finite. Now we have already talked about this, that the equation that we have written earlier is called the principle of virtual work or the weak formulation, as we would like to call. But for engineers, especially people in mechanics, principle of virtual work is something that we know or we are aware of. So we may go ahead with that formulation, but they both mean the same thing. Okay, let us now concentrate on the equations that we have obtained earlier. There you see that we have this pair Ea du dx and delta u or w occurring together, and we said that if the force is specified, we let delta w or delta u or w to be anything, and when the displacement is specified, we are going to set delta u or w equal to 0. When a force is specified at an end, that boundary condition is called the natural Neumann or force boundary condition. At the end where u is specified, that is where we are going to fix our delta u equal to 0, that end is called an essential, Dirichlet or displacement boundary condition. This will generalize to 2 or 3 dimensions in the future. So these definitions should be kept in mind. That is, we are going to generally call them by the name Neumann or natural, or essential or Dirichlet. Now, why is the force boundary condition a natural boundary condition? If we go back to our equation that we have written, equation of the weak formulation, you see that the force appears naturally in the formulation. That is, it is sitting there in the right hand side of the equation. That's why it is called a natural boundary condition. While the displacement being fixed at an end is not explicitly appearing in our weak formulation. That is, it has to be enforced by forcing delta u equal to 0. So that's why it's called an essential boundary condition. That is, it has to be forced in. Okay, so this can now be rewritten, whatever we have developed earlier, using a different concept. But we'll get the same set of equations that we have obtained earlier. So next we'll go to a new concept from which we can develop our equations all over again. For that we'll need to do a little bit of homework. That is, we have to look at this variation of ux, certain more properties of it. For example, if I take variation of du dx instead of u of x, this will be equal to the derivative of the variation of u. Similarly, if I take variation of u squared, it will be equal to twice u of x into variation of u of x, and so on. So variation essentially works in principle like the derivative, but it is not the derivative because we are talking of perturbing a function, not taking differential or the derivatives of a function at a point. So using these properties, we are going to develop the next thing. What we are going to define now is something called a functional. What is a functional? A functional is a function of a function. So it will take, let me call I as the functional, it will take a function u of x and it will return to me a number. Which is I u of x. So I give one function u of x, I'll get a number. I give another function u of x, I'll get another number. For example, I may define various functionals like this. Integral from x equal to 0 to L EA du dx whole squared minus integral x equal to 0 to L fu dx minus p u at x equal to L. This is a functional where p, f, ea are given to me a priori as material data or the input data to the boundary value problem that has to be supplied. So now if I give you a function u, then this integral is going to return me a number, this part is going to return me another number, and this part is going to return to me another number, and the sum of it will be iu, which is a number. Now I change the function u, put some other function w there, I'll get another number. So this is called a map of the function to real numbers. Okay, so when I have iu, I can also define another functional iu by another example. Let's take is this half x equal to 0 to L. We are not going to elaborate on it now, but this is essentially related to our mechanics problems of interest. Minus, I may have f at the end x equal to L, W at the end x equal to L. This can be another functional of interest. So now given a functional, we will also define the variation of the functional, delta IU. This variation will be given by definition as limit of alpha tending to 0 of I u plus alpha delta u minus I of u whole thing divided by alpha. So what do I have? Instead of u, now I put u plus alpha delta u into my expression for the functional, evaluate that number, from that subtract the number corresponding to I of u, divide that by alpha, take the limit of alpha going to 0, this is called the variation of u. Now what we can do is that we can define for the various problems of interest, boundary value problems, in many cases, not always, we can define this functional IU. And given this functional IU, we will see that the variation of IU, when it is set to 0, also gives us the solution to the boundary value problem that we are after. So let us now go back to our variational formulation, the weak formulation that we have given earlier, or the principle of virtual work for the model problem of interest, and rewrite that in the setting of, if we can, of a functional IU. So if we have that formulation, we have integral x equal to 0 to L EA du dx d delta u dx dx. This will be equal to, by our definition of the variation, keeping EA as a given constant. We cannot vary EA because this is something that is supplied to us. So we can write it as integral x is equal to 0 to L EA into half of delta of du dx whole square dx, which we can write as half of integral 0 to L, we'll put delta of EA du dx whole squared dx. Okay. So the first term essentially can be written as, but in a more compact way, integral delta of half of integral of x equal to 0 to L EA, if I want to write it now using a simpler notation, EA derivative of u with respect to x squared dx. Similarly, the other term which we had, integral of f delta u dx can be written as delta of, from x equal to 0, delta of integral of x equal to 0 to L f u dx. And the term p delta u evaluated at the point x equal to L is equal to delta of p u evaluated at x equal to L. So by collecting all the terms together, what we end up getting is delta of half of integral x equal to 0 to L EA u comma x squared dx minus integral x equal to 0 to L f u dx minus p u at x equal to L. This is equal to 0 from what we have said earlier. Okay. So then this term within the square brackets is now our functional I of u. So what we have done is said that the variation of I of u is equal to 0 is also the weak formulation or the principle of virtual work we had given earlier. Now can you tell us what is I of u for the problem that we have taken? I of u, if you look at this term in I of u corresponds to the strain energy u for the structure. The remaining part corresponds to the potential of the external forces. So what we have, this I of u for us is nothing but the total potential energy pi of the structure. And we know very well that the minimizer of the total potential energy is the function which solves our model problem. So we can pose this again as, let us write it in a concise way, del I of u is equal to 0 is also equal to del of the pi of u. Now because this same equation can be obtained by taking a variation of the potential I of u, which in our case corresponds to the total potential energy associated with the system. This is also called a variational formulation. So let us check that we have written that delta I of u is given by definition as limit of alpha tending to 0 of I of u plus alpha delta u minus I of u whole thing divided by alpha. Let us see if it is really giving us that equation back, because we simply rewrote everything in terms of that potential and we said that yes, this is equal to 0. So let us take that potential that we have defined earlier, I of u, and in that we put u plus alpha delta u. So what will we get? This will be equal to half integral x equal to 0 to L EA u prime x plus alpha delta u prime x whole squared. Okay, I'll rewrite it here. This is equal to half of, let's erase this, 0 to L EA u prime x plus alpha delta u prime x whole squared dx, and the other part will be minus integral x is equal to 0 to L f into u plus alpha delta u dx, and finally let's go to the next page, minus p u at L plus alpha delta u at L. From this, if we subtract IU, what do we get? I will get integral x is equal to 0 to L EA into half I'll have in front 2 alpha u comma x delta u comma x, okay, plus alpha squared delta u comma x whole squared dx minus integral x is equal to 0 to L f alpha delta u dx minus p alpha delta u at x equal to L. Now we said that we are going to divide this thing by alpha. So when you divide this thing by alpha, this guy will go, here we will be left with a single term alpha, and here also this person will go, this one will go. So what we have, when we take the limit, then all the terms which after division by alpha have an alpha sitting in front will go to 0. They will disappear. All the terms with no alpha in front will be what we will be left with. So this will be equivalent to writing as delta I of u is equal to half of equal to 0 to L EA u comma x delta u comma x dx. So the 2 and the half will cancel, minus integral x is equal to 0 to L f delta u dx minus p delta u at x equal to L, and this has to be equal to 0. And you see that we have obtained our principle of virtual work by this approach too. So the variation of the functional has given us our principle of virtual work. Okay, so what we have said is that we obtained in our formulation the variation of I of u is equal to 0, or we say that the solution to the problem given by u of x, to the model problem, is an extremizer of I of u. Now whether this extremization is a minimization or a maximization or a point of inflection is not something that we are going to look at. So as soon as ux is an extremizer, then the extremizer solves the model problem of interest. Okay, so next let us introduce a few notations. What we are going to call this one, bu v is equal to integral x equal to 0 to L EA du dx dv dx dx. This term is given by this notation. This is called a bilinear form. Why is it bilinear? That if I look at bu plus alpha w1 v, this will be equal to b uv plus alpha b w1 v. That is, it is linear in the function u. Similarly, if I put b u v1 plus alpha v2, this will be equal to bu v1 plus alpha b u v2. That is, it is linear also in v. That's why it is linear in both the functions which give us this number buv, so we call it bilinear. Similarly, we can introduce another notation f of v, which is equal to fv dx for our model problem minus p v at x equal to L, sorry, plus pv at x equal to L. This quantity is called a linear functional. Just like we have defined the functional earlier, what f does, it takes the function v and gives us a number fv. And why is it linear? It is linear because if I now take two functions, alpha 1 v1 plus alpha 2 v2, f of that, if you put it here in the expression that we have taken earlier above, it is equal to alpha 1 f of v1 plus alpha 2 f of v2. That's why it's called a linear functional. So what happens using this notation, now we have made our writing of these equations terse. And instead of v, if we substitute as v with delta u, then I'll get BU delta U is equal to f of delta U, which is nothing but the principle of virtual work or the weak formulation or the variational formulation that we have obtained. Now, what we are going to do is, okay, we have obtained this as our equation that we have to solve in order to get U. There should be various questions that one should ask. Tell me that what do we mean by delta U in this case, and how are we going to get to U? How to obtain U? As a function of x. Now obviously, if we knew how to get a closed form solution to the boundary value problem that we have considered earlier, then we would not have had to come to this stage at all. So what we would like to do is, we would like to obtain a series solution to U. So what we are going to do is, we are going to represent U as a series in terms of, in this form. In this series, what we would like to obtain is the coefficients of the series, provided we choose these functions phi I of x, which you can call as the so-called basis functions. If you can choose these basis functions properly, then the linear combination of these basis functions will form our solution U of x, and we'll assume, let us assume for the time being, that this series is convergent. Implicitly we have assumed that the series converges to U of x at every point. So now the job is to find these coefficients AI. How can we use what we have done here to find the coefficients AI? That is the first question. Secondly, we do not want to find in all cases all the infinite coefficients. We will be happy by getting something called the approximate solution. That is, we will now take, instead of the full series, a truncated series, where I will have n terms un of x. So this is now a so-called truncated series. So again, now in this truncated series, if we can find all these coefficients ai, if they are known, then given these functions phi I, then we have obtained our approximate solution or the truncated solution. The question is, how do we choose these phi i's? So one thing that these phi i's have to satisfy is that the phi i's have to be linearly independent. Which means, the linear independence in our case means that, let's say that I take this finite series only and I put is equal to, the linear combination is equal to 0 for all x which is in this range 0 to L. You can say including the endpoints. Then linear independence means that if this is what is required, then these AIs will come out to be 0. All of them, then all the AIs will be equal to 0 trivially. So if this happens, then we say these functions phi I are linearly independent. So in forming this series, we need these linearly independent terms. Then we would like to now put this in our principle of virtual work or the variational formulation. Let us go by the variational formulation. That is, instead of asking for delta I of u equal to 0, we are now going to say delta I of u of n is equal to 0. Okay. So when we say delta I u of n is equal to 0, then what do we get? So this will be written as integral x is equal to 0 to L EA dun dx d delta un dx dx is equal to integral x is equal to 0 to n f delta un dx plus p delta un evaluated at the point x equal to L. So now what we have done, we have replaced, instead of u, we have put un, and we say that we are looking for the function un, which is an extremizer of this I that we have defined for our model problem of interest. So the question is, what is delta un? Okay. So let us see what is delta un. Delta un for us will be equal to delta of sigma of I is equal to 0 to n ai phi x. Now we have chosen what is our phi I. That is, each of these phi i's are known functions that we are going to use to construct the series. So the delta of un will become sigma I is equal to 0 to n delta of ai into phi I of x. So you see what has happened, that the variation of un is given in terms of the linear combination of the variations of the ai's. So what we will do next is that, fine, if it is given in terms of the variations of these ai's, each of these delta ai's can be varied independently. What does this mean? That is, because this delta u is something that is under our control, that is, it is something that we are specifying, we can choose delta a1 equal to 1, let's say, and all other delta ai's equal to 0, that will be 1 delta u. Similarly, I can choose delta a2 equal to 1 and everything else equal to 0, that will be another delta un. So with this various choices of delta un, by fixing these values of delta ai, we should be able to construct various forms of this delta un. Now what we will do next is, we are going to now vary these independently, and what we will do is we will end up getting, by variation, n plus 1 equations which are simultaneous equations in terms of the n plus 1 variables ai. Now there is another thing that we should note. Let us take the model problem that we have posed. For that model problem, we need delta u of n at 0 is equal to 0. This also we have to specify. So this is another condition that is going to come on these delta ai's. Because why will it be on delta ai's? Because delta un at 0 is equal to summation delta ai phi I evaluated at 0. I is equal to 0 to n. So what we are going to do next is, we are going to look at this in a detailed way, and we are going to pose something called the Ritz method, where we are going to choose particular forms of these phi i's specifically for the model problem that we have taken, and we are going to basically formulate the problem in terms of this truncated series and solve it by minimizing the total potential energy with respect to the coefficients delta ai's. So what we'll do in the next class is we'll take n equal to 2 or n equal to 3 with some specific forms of f and p and solve the problems and see what are these coefficients. So in the next class we are going to develop the Ritz method for the model problem that we have taken, where the n term series that we are going to use for the approximation of u of x will be given in terms of very specific functions. We have said that we would like our delta un as well as un to satisfy the 0 condition at x equal to 0. So let us take these phi i's to be functions which are x to the power of I, that is x to the power of 0 which is 1, x to the power 1 which is x, x squared, x cubed, so on up to x to the power of n. Then unx is a summation of ai x to the power of I. So when we put un at 0 is equal to 0, then automatically a0 comes out to be equal to 0. So once we have a0 equal to 0, then our series will be written in terms of summation I is equal to 1 to n ai xi, and what we will need to do is to develop sufficient number of equations to obtain these ai's. That is, we need n equations in terms of the n unknown ai's. Once we get them, then we will get the solution, and through plots of solutions for certain boundary value problems that we will take as typical examples, we will show that this method does very well for certain classes of loading, and also will bring out the drawbacks of this method, which we are going to exploit to develop the finite element method as a tool to overcome these drawbacks.